Well, hello there. Today we're going to do section 10.5. It's on binomial expansion, and I haven't been doing this, but it would be probably a good idea if you print out these notes ahead of time. I just thought this one just had a lot of underlying work to explain. So if you don't want to, that's fine. You can just copy down the essential parts that you think you need. Anyway, so binomial expansion. So first you have to remember from Algebra 2 the formula for combinations. So remember when somebody writes this, n choose r, so if somebody wrote 5 choose 3, what we're going to do is n factorial, that number factorial, over n minus r factorial over r factorial. So remember that exclamation point means factorial. So if you write 5 factorial or something like that, it means to do 5 times 4 times 3 times 2 times 1. All right, and another good thing to notice here is that when you're dividing factorials, a lot of times it's easier. Let's say that you would have 20 factorial and you're dividing it by 18 factorial. All right, so 20 factorial is 20 times 19 times 18 times 17 and so on. And then 18 factorial is 18 times 17 times 16 and so on. So basically what's going to happen is everything 18 and down cancels with everything 18 and down here. So you can just be like, oh, it's 20 times 19. And then it makes it a little bit easier. We're not going to have any ones that large here, but just so you know for future. All right, so the combination formula tells you, remember that it tells you the number of ways to order or choose r items from n items. Okay, so assuming the order doesn't matter. If you want the order to matter, then remember that's permutations, not combinations. So for example, let's say you have these 5 flavors here. How many ways are there to choose 3 of these Jolly Ranchers from the 5 flavors? Well, you would do 5 choose 3. Now another way that you see 5 choose 3 written is you see it written like this right here, kind of like it's almost like in a vector format. But anyway, that means 5 choose 3 as well. And so I would do 5 factorial over 5 minus 3, which is 2 factorial. And then the r factorial is right here, 3 factorial. So when I work this out, I'm going to use 3 factorial to reduce this down a little bit. So I got 5 factorial, so that's 5 times 4 times 3 times 2 times 1. In the bottom I have 2 factorial, so that's 2 times 1. And 3 factorial is 3 times 2 times 1. So you see I'm going to cancel those out. And so what I have left is 20 divided by 2, which is 10. So there are 10 different choices of colors that you could have, group them together. So, you imagine, oh, I could take green, yellow, and purple. Or then maybe I could take green, maybe this is watermelon and yellow. So those kind of things, right? So each thing would be a different group of flavors, right? So let's take a look. Now you can do combinations on Desmos. You can also do them on your calculator. Remember on your calculator, usually what you do is you press the number first, like 5, then you press the math button, you go over to probability, and then you choose the one that says NCR, and then you enter after NCR appears, then you press 3, and then you go ahead and do that. If you're going to do it on Desmos, if you go under on the functions, if you go to stats, then there is an NCR button. And so when you do the NCR button, it'll appear. And then after that, it puts a parenthesis. So you would put 5, 3, and it would give you the answer of 10. So anyway, that's how you do it on Desmos and your calculator. All right, so let's go on. We needed these things for what's called Pascal's triangle. Now I alluded to this before, and the Pascal's triangle goes like this. If you use those combinations, the numbers in Pascal's triangle come from the combination answers. So 0 choose 0, this first one right here. So imagine you have 0 things and you're choosing nothing. Well, great, you have one choice, choose nothing. 1 choose 0, so you have one thing, you're choosing none of them, that's 1. And 1 choose 1 is also 1. Now, there's a couple things to note here. All these guys right here, 2 choose 0, 3 choose 0, 4 choose 0, 5 choose 0. There's only one way to do something if you're not going to choose anything at all, and that's just to not choose something. So all these have an answer of 1 all the way down here, all right? And also these ones back here, there's only, if you're going to do 1 choose 1, 2 choose 2, 3 choose 3, 4 choose 4, 5 choose 5. If you have 5 things and you take all 5 of them, that's one way to do that. You take all 5. So all these are also 1. There's also some more obvious answers in here, and that's this little diagonal right here. when you choose one of something, like if you have 2 items and you're choosing one of them, that means that you have 2 choices. If you have 3 items and you choose one of them, that means you have 3 choices. 4 choose 1 is also 4. And 5 choose 1 is 5, and so forth. So if you're ever choosing one, even if you have 20 choose 1, well, that's 20 choices because you're going to pick one of those 20 things, so you have 20 different choices. Okay. All right. Now the other ones you might take in your input in your calculator, but what's going to happen here, you can also, I don't know if you remember from before, I showed you that these little triangles here, like for instance, if I want to get this number here, it is the addition of these 2 things. So you see how 1 plus 2 equals 3, 1 plus 3 equals 4, 1 plus 4 equals 5. Well, why don't we try and do that? 2 plus 1, that number would be 3. And then if I wanted to do 3 plus 3, that's how Pascal's triangle works. This is 6. This one would be 4. This one would be 10. Add those 2 triangles, I get 10, and these 2 I get 5. So you can keep on filling these other rows of triangles out, and you can keep doing that. 1s go down the sides. All right, 1 plus 5 is 6 here. 5 plus 10 is 15. 10 and 10 is 20. 10 and 5 is 15. And you also notice a little pattern. It as you go along, it kind of rises up to a crescendo and then it goes back down in the same manner. So you'll notice some matches over there or some common themes. All right, I got 7 here, then 21, then 35, then another 35, and then 21 again, and then 7 again. Okay, so if you were going to use this to expand a binomial, remember a binomial is something with 2 things in it, added together, like a binomial expression. Well, if I was going to do x plus y to the 0 power, well, anything to the 0 power is 1. If I was going to do x plus y to the first power, and it can be anything, it doesn't have to be x plus y, you would get x plus y, right? Well, these numbers right here, the 1 and the 1, those are the coefficients of my expansion, my 1 and my 1. Well, if I was going to do x plus y squared, you'll see on the next page, the coefficients are going to be 1, 2, 1, and so forth. And so these rows of this Pascal's triangle have to do with the power that you're raising it to. So if you're doing x plus y to the 3rd, you use the 4th row of the Pascal's triangles because it's the 1st row, 2nd row, 3rd row, 4th row. All right, so if you wanted to do something to the 4th power, realize you're using the 1, 2, 3, 4, 5th row, okay? And so we're going to see that on the next page a little bit, and we'll come back and forth to this. All right, so let's do x plus y squared. Now, I taught you the little trick to doing that. Oops. Remember, you do x squared, so x squared, then you multiply these 3 things together, so I get plus 2xy, and then plus y squared. All right, so that's exactly what we were saying. Look at the coefficients right here, 1, 2, 1. And so that's exactly matching what this is right here. All right, so x plus y to the 3rd. So to prove to you that this works this one time, I'm going to take the last answer, my x squared plus 2xy plus y squared, and I'm going to multiply it by x plus y. All right, so I'm going to do x times all these pieces and get that answer. So that would be x to the 3rd plus 2x squared y plus xy to the 2nd. All right, and then I'm going to do y times all these things, all right, and get that answer. So it would be x squared plus 2xy squared plus y to the 3rd. So let's collect my like terms. I have x to the 3rd, and let's see right here. I got 2x squared y, I have another x squared y there. So I'm going to say I have 3 of those x squared y's. And then I have xy squared and another xy squared there. So again, I have 3 of those xy squared. And then finally, I have the y to the 3rd. Sorry. All right, so I want you to notice here, you have the coefficients. You have a 1 right here, you have the 3, 3, and 1. So that's exactly like you were supposed to get right there. But also notice what's going on with the variables, all right? So what's happening here is the x's are growing are starting at x to the third and dwindling down, the y's are growing. So what happens when you do binomial expansion is whatever is in the first spot gets the highest power first, but then notice it dwindles down to nothing over here. And then whatever in the second spot, it doesn't exist in the first piece, but then it starts raising. That's power 1, power 2, power 3. So as one goes down, the other one goes up. So let's try to do this one without doing all this multiplication. So x plus y to the fourth. So I'm going to look right here. That's these coefficients, 1, 4, 6, 4, 1. So I'm going to space those out a little bit and write them down. So I have 1, 4, 6, 4, and 1. So, like I said, my x is starting at x to the fourth, so x is being taken to the fourth power. Then the next term, it'll be to the third power. Then the next one, it'll be to the second power. The next one will be to the first power. And finally, it'll be to the 0 power. So it starts high and goes low. Then the y starts at 0, but it starts to raise to 1, and then raise to 2, and then finally to 3, and then lastly to 4. All right, so everything's positive in this problem, so these are all pluses here. Okay, and then we have our answer. We would have x to the fourth plus 4 x to the third y plus 6 x squared y squared plus, I got 4x y to the third, and then plus finally y to the fourth. Okay, and so there's your expansion. That's kind of a simple one, but you know. And over here I have a question for what's the middle term. So in your your math space, it's going to ask you some questions like this. You don't have to do the whole problem. It's just asking you for the middle term. So if somebody asked me my middle term, I'd be like, oh, there it is right there. Okay. All right, so let's do one that's just like a full-on problem, and then we have the last few little examples to do right here. All right, so 2x minus 1 to the fifth power. So my sixth row, I guess I would say, when I'm doing fifth power, I'll be using this right here. So I have 1, 5, 10, 10, 5, 1. So let me jot that down. 1, 5, 10, 10, 5, and 1. I'm going to write my stuff underneath it because it's a little bit large. All right, so underneath this 1, I'm going to write the things next to it. I would have 2x to the fifth power, and then the next one I'd have 2x to the fourth power, and then 2x to the third power, 2x squared, 2x to the first, and then finally 2x to the nothing. I don't really have to write that down, but anyway. Now my negative 1, so I have to be careful here. It's a negative 1, so I'm going to take that. So negative 1, first of all, to the 0. And I have negative 1 to the first, negative 1 to the second, then negative 1 to the third, then negative 1 to the fourth, and finally negative 1 to the fifth. All right, and so remember this 1, 5, 10, 10, 5, 1, those are multiplying by these pieces. So let's see what we got. So I have 1 times 2x to the fifth times negative 1 to the 0. Well, 2x to the fifth is going to be 32x to the fifth, so times 1, and then negative 1 to the 0 is 1 again. So I have 32x to the fifth. My next term, I have 2x to the fourth, so that's 16x to the fourth, times 5, so that's 80x to the fourth, and then I have times negative 1, so I'm going to get negative 80x to the fourth. And for the next piece, I have 2x to the third, so that's 8x to the third, times negative 1 squared, so that's 1. So I have 8x to the third times 10, so that's plus 80x to the third. All right, for the next piece, I have 2x squared, so that's 4x squared. Negative 1 to the third is going to make that negative 4x squared, and then times 10, so I have negative 40x squared. And then the next piece, let's see, I have 2x times 5, so 10x. Negative 1 to the fourth is positive, so positive 10x. So what's happening here, the powers of 2 are affecting these coefficients. All right, and then finally I have negative 1 to the fifth, so that's a negative 1. 2x to the 0 is positive 1, so I basically just get a negative 1 right here. And that's the expansion of 2x minus 1 to the fifth. And that way you don't have to sit there and FOIL it out, which would take a lot longer. All right, the next part, this piece we're just going to find little pieces. So this one says find the coefficient of the term x to the sixth. So notice I have something a little different here. It's not just like a simple x right there. So if this is going to be x to the sixth, so you can expand this, the whole thing. I mean, you're going to get a bunch of terms. In fact, you're going to get 13 terms. Like whatever power this is, you get one more than that for the number of terms. But I don't want to do that. I mean, ugh. And so what I want is the part that produces x to the sixth. So remember, here's my setup. All these little pieces of my problem up here, all these little pieces right here were made by doing this. I would have this power, so I'd have 12, choose some number. I would have x squared to some power, and then I would have 3 to some power. So let's choose what the powers should be. So if I put, let's see, I want x to the sixth, so if I put a 3 right here, 2 times 3 is 6. Well, that means there would be a 3 right here. And then, you know, I don't know if you noticed, but these powers right here, 2 plus 3, 2 plus 3, 1 plus 4, 0 plus 5, they all add up to the exponent. So that means that I need 3 plus this to add up to 12. So that must be a 9 then. All right, so all I have to do is work this out. So I have 12 choose 3, so let me grab my calculator. So that would be 220. That would be x to the sixth, and then I have 3 to the ninth. Well, 3 to the ninth is 19,683. All right, and then I'm multiplying that by 220. So, oh my goodness. This is 433,0260. So 4,330,260 x to the sixth. All right, so there we go. So what is the coefficient? So I would answer you, the coefficient is 4,330,260. All right, next one. What is the seventh term in the expansion of this problem? So 10th power. So remember that when you're looking at Pascal's triangle, your first term is right here, second term, third, fourth, fifth, sixth, seventh, and so on. So if you're doing the first term, so that would be with 0, second term has a 1, third term has a 2, fourth term has a 3, fifth term has a 4. So if it was the seventh term, it would have a 6. So it'd be 7 choose 6. I'm sorry, it'd be 10 choose 6. Sorry. So anyway, so if I'm trying to do this seventh term, since I was starting with 0, I'd be doing choose 6. So here we go. I got 10 choose 6. So that means I'm going to have 2x to the third to the sixth power, and then I have -1 to the, has to add up to 10 to the fourth power. All right, so here we go. 10 choose 6 turns out to be 210. 2 to the sixth is 64, so I got times 64, x to the 18th. And then my -1 to the fourth is just a 1. So it turns out that I have 13,440 x to the 18th. And that is the seventh term in the expansion. All right, so one more thing, it's not, so I guess you could stop now if you're not interested, stop the video, but I thought this would be cool to show you if you want to expand a complex number. So remember before we had to use de Moivre's theorem, and remember we had to find r and find theta, and it was like this. We had like z to the n, we did r to the n, and then cosine of n theta plus I sine n theta. Remember that when we wanted to do a complex number to a power and it turned out gross and we needed our calculator? Well, let's do this problem, 2 plus 3i to the fourth, using binomial expansion. So we're going to do that one there, and that's our last problem. So we want 2 plus 3i to the fourth. All right, so using that row right there with the fourth power, I got 1, 4, 6, 4, 1 for my coefficients from the binomial expansion. And then I'm going to have my 2. Well, the first time it's the fourth power. Then I got third power, second power, first power, and finally 0. And then I have 3i, so imaginary number, 0 power, and 3i, 1, and 3i, 2, and 3i, 3, and 3i to the fourth. All right, so remember your powers of I. I is just I squared is -1, I to the third is -I, and I to the fourth is just 1. All right, so here we go. So this guy right here, 2 to the 4th, that's 16. 3i to the 0 is 1, and I have 1, so I got 16 from here. Here, I have 4 times 2 to the 3rd is 8, and then I have basically 9i squared. All right, so this part right here, 32 times, oh, that was the first power. Sorry, I couldn't read that. So I don't have that, I just have 3i. So I have 32 times 3, so I have 96i. So I got 16 plus 96i so far. And then here, I have 4, 2 squared is 4, 4 times 6 is 24. Then, so I have basically 24 times, this is 9i squared. So 24 times 9 is 216. All right, so I have 216, and remember I squared is -1, so I'm just going to write negative 216. All right, here, let's see, I have 4 times 2, so I have 8, and then 3i to the 3rd, so that's 27i to the 3rd. All right, so 8 times 27 is 216. And then I to the 3rd is worth -i, so I'm going to put a negative and an I there. And finally, 2 to the 0 is 1, 1 up top, and 3i to the 4th. So I basically have 81i to the 4th. Well, I to the 4th is just worth 1, so that's plus 81. All right, so I'm going to combine my like terms. I got, let's see, 16 minus 216 plus 81. Put those together, and I get -119. And then I have 96i minus 216i, and then I have -120i. So that is the expansion of this. And it's easier or not easier. I think it's better because it's, you don't really have to use your calculator much. Or, you can just type this in the calculator. It'll tell you to confirm it. But I thought that was kind of cool. All right, and that's it. I'll talk to you later.